Most people imagine the solar system as a flat, empty disk, but that picture is only half true. Above and below it are invisible layers of ancient ice, interstellar gas, dead star dust, and dark matter that may make up 85% of the Milky Way's mass. Before we go deeper, take 1 second to like and subscribe, because this journey changes how we see our place in space. Now, we begin. Every textbook, every documentary, every classroom poster you have ever seen, the solar system looks the same in all of them. A perfect flat disk, planets lined up in neat rows on a single plane, like marbles rolling across the same pane of glass. Mercury close in, then Venus, Earth, Mars, and the giants fanning outward in a clean, orderly sequence. Everything flat, everything arranged, everything with a clear top and a clear bottom. That image has been burned so deep into the human brain that most people picture the solar system the way they picture a plastic model hanging from a classroom ceiling, tidy, predictable, everything exactly where it belongs. And honestly, that picture is not wrong. It is just catastrophically incomplete. 4.6 billion years ago, a massive cloud of gas and dust began collapsing under its own gravity. As it collapsed, it started to spin. Conservation of angular momentum forced that spinning cloud to flatten the faster it pulled inward, the thinner it became, spreading into a rotating disk exactly the way a ball of pizza dough flattens out when a chef spins it in the air. Planets formed from the material already inside that disk. So naturally, they all ended up orbiting on roughly the same plane. Astronomers call this the ecliptic plane. Basic physics? Clean logic. The story seems closed. Then Mercury ruins everything. Mercury is the closest planet to the Sun. If any planet should be locked firmly into that original disk, it should be the one sitting deepest inside the Sun's gravitational grip. And yet Mercury's orbit is tilted 7 degrees off the ecliptic plane. 7 degrees does not sound dramatic until you remember the entire system was built from a flat disk. Any tilt at all is a deviation that demands an explanation. Mercury is small and light. During the violent, chaotic early period of solar system formation, the gravitational influence of Jupiter and Saturn was relentless. Those two giants were slinging smaller bodies in every direction across the young solar system. Mercury, the lightest object sitting closest to the center, caught the worst of it, like the smallest marble on a crowded table, getting knocked sideways every time one of the large ones rolls past, while the heavy ones continue straight ahead undisturbed. Now you might be thinking 7 degrees is barely anything. Fine, try 17. Pluto sits tilted 17 degrees off the ecliptic plane, and before you reach for the obvious objection, yes, Pluto was reclassified as a dwarf planet by the International Astronomical Union in 2006. But that classification does not dissolve the question. Here is what actually matters. Pluto formed from the same original protoplanetary disk as everything else in this solar system, the same flat, spinning disk. So why does it orbit at an angle that looks like it belongs to a completely different system? The answer is Neptune. Over billions of years, Neptune's gravitational influence acted on Pluto through repeated cumulative interactions, slowly pushing its orbit further and further from the plane, like a pendulum being nudged just a little harder on each swing until the deviation becomes impossible to ignore. You might also be thinking Pluto is a dwarf planet, so it does not really count. But that objection is exactly the kind of instinct this story is designed to break. The question is not about classification. The question is about what the orbital data is telling us about the structure of the solar system itself. And what 17 degrees of tilt on an object that formed inside the original disk is telling us is this: the solar system is far less orderly than the classroom model suggests. Pluto had already been stripped of its planetary status, demoted in front of the entire scientific community, asked to leave the table, and now it orbits at 17 degrees off from everyone else, like someone who gets escorted out of the dinner party and then stands outside the window, watching at a tilt, as if to prove they were always different anyway. But here is the crucial thing. Mercury at 7 degrees, Pluto at 17. These are deviations, yes, real ones, but both objects are still operating in the general neighborhood of the ecliptic. They tilt away from the plane, but they are still recognizably part of it. They are still products of the same original disk. What comes next is not a deviation from the plane. It is a complete rejection of it. Some objects in this solar system arrive from directions that are not 7 degrees off the ecliptic, not 17 degrees, not even 45. They come from angles that are fully 90 degrees perpendicular to the ecliptic plane, driving straight down through the disk like a needle being pushed directly through the center of a spinning vinyl record. Top to bottom, no apology, no relationship to the flat highway the planets call home. These are long-period comets, and they do not arrive from one perpendicular direction. They arrive from every direction in three-dimensional space, above the disk, below it, from the sides, from angles that correspond to no particular plane at all. Astronomers have tracked hundreds of them, mapped their trajectories backward to their point of origin, and the pattern is unmistakable. These objects are coming from a source that is not a disk, not a ring, not a flat structure of any kind. Their source surrounds the solar system equally from every direction at once. That is the logical trap the data sets. If long-period comets arrive uniformly from all directions in three-dimensional space, then whatever they are coming from must be a three-dimensional structure, a shell, a sphere, something that wraps around the entire solar system in every direction simultaneously. And that conclusion, forced entirely by the geometry of comet trajectories, is what led Dutch astronomer Jan Oort in 1950 to propose the existence of what is now called the Oort Cloud, a vast, roughly spherical shell of icy objects completely enclosing the solar system from every side, stretching out to distances so extreme they approach the gravitational territory of neighboring stars. No one has ever seen it directly. Not one telescope on Earth or in space has produced an image of an Oort cloud object sitting in its natural orbit. The distances involved make direct observation essentially impossible with any instrument currently in existence. And yet the Oort cloud is not a fringe hypothesis. It is one of the most confidently held conclusions in solar system science, accepted not because anyone photographed it, but because the alternative explaining where hundreds of comets with isotropic, all-direction trajectories are actually coming from has no answer that survives scrutiny. You know the Oort cloud exists the same way. You know a strong wind is blowing when you are standing in a windowless room. You cannot see the wind. You can only see what the wind does to things you can see. The comet trajectories are the bending trees. The Oort cloud is the wind. But neither Mercury nor Pluto are the most radical rebels in this story. There are things that plunge into the solar system from directions that are completely perpendicular, like a needle driving straight through a spinning vinyl record, and they reveal the existence of a structure no one has ever directly seen. Start with a simple thought experiment. If the solar system were a truly flat system, a pure disk and nothing else, where would comets come from? The answer is obvious. They would come from the disk. They would arrive from the same plane as the planets, the same general direction, the same narrow band of sky. Like cars on a highway, traffic moves along the road, not through the ceiling. Short-period comets, the ones completing an orbit in under 200 years, actually do behave this way. Halley's Comet is the most famous example. These objects originate from the Kuiper Belt, a disk-shaped region of icy bodies beginning just beyond Neptune at around 30 astronomical units from the Sun and extending to roughly 50 astronomical units. The Kuiper Belt is flat, consistent with the rest of the solar system's disk. So the comets it produces arrive in roughly the ecliptic plane. The model holds. The car stays on the road. Then there are the long-period comets, the ones that take thousands, tens of thousands, even millions of years to complete a single orbit. And these comets do not care about the ecliptic plane at all. They arrive from every direction in three-dimensional space, from directly above the disk, from directly below it, from angles precisely perpendicular to the plane the planets orbit on. The car is coming through the ceiling, through the floor, through the walls, from every surface of the room simultaneously. Astronomers have tracked hundreds of these objects, mapped their incoming trajectories backward toward their origin points, and the distribution is unmistakable. These objects are coming from a source that surrounds the entire solar system in every direction equally, not a disk, a sphere. In 1950, Dutch astronomer Jan Oort looked at exactly this data and drew the only conclusion the geometry allowed. If long-period comets arrive uniformly from all directions, their source must be a vast, roughly spherical shell, completely enclosing the solar system from every side. This became the Oort Cloud, a structure that, in the 75 years since Oort proposed it, has never once been directly observed, yet remains one of the most confidently accepted features in all of solar system science. No image, no direct detection, no spacecraft within reach. Iron-solid scientific consensus. The reason is the same reason you know a strong wind is blowing even when standing in a sealed room with no windows. You read the evidence it leaves behind. The orbital trajectories of long-period comets are the swaying trees. The Oort cloud is the wind. The logic connecting them is so airtight that rejecting the cloud would require explaining where else those comets could possibly be coming from, and no alternative has ever survived scrutiny. Now consider the scale of what Oort proposed, because this is where the comfortable mental model of the solar system completely falls apart. Neptune, the outermost planet, orbits at roughly 30 astronomical units from the Sun. 1 astronomical unit is approximately 93 million miles, the average distance from Earth to the Sun. 30 astronomical units is already a distance that strains imagination. Voyager 1, launched in 1977 and traveling at roughly 38,000 miles per hour, took more than 12 years just to reach Neptune's distance. The Oort cloud does not begin at 30 astronomical units. Current models place the inner edge of the Oort cloud at somewhere between 2,000 and 5,000 astronomical units from the Sun. The outer edge extends to approximately 100,000 astronomical units. 100,000. Neptune sits at 30. The Oort cloud's outer boundary is more than 3,000 times farther out. A comparison that actually lands if you shrink the entire solar system from the Sun to Neptune down to the size of a single quarter coin sitting in your palm. The Oort cloud surrounding it would extend outward to cover an area roughly the size of a full NFL football stadium. The coin is the solar system from every textbook, every poster, every documentary you have ever seen. The stadium is the actual solar system. And it gets more disorienting. Proxima Centauri, the nearest star to our Sun, sits at a distance of approximately 268,000 astronomical units. The outer edge of the Oort cloud at 100,000 astronomical units reaches nearly 1/4 of the way to the nearest star. The solar system does not end at Neptune. It does not end at the Kuiper belt. It ends, if it ends at all, in a frozen shell that nearly grazes the gravitational territory of another star entirely. How did the Oort cloud form? The same culprits responsible for Mercury's tilt. In the early solar system, Jupiter and Saturn were already enormous, and their gravitational reach was relentless. Small icy bodies that wandered too close to either giant got flung outward at enormous velocities, not out of the solar system entirely, but far enough to settle into extremely distant, loosely bound orbits at the very edge of the Sun's gravitational influence. This happened billions of times over tens of millions of years. The result was the gradual accumulation of a vast frozen reservoir at the outermost boundary of everything, containing an estimated several billion to several trillion individual objects, each one a preserved fragment of the raw material from the solar system's formation 4.6 billion years ago. Every long-period comet that blazes across Earth's sky is one of those ancient objects, disturbed from its billion-year resting place by a passing star or an internal gravitational nudge, falling inward on a journey that will take it from the edge of the solar system all the way to the sun's neighborhood. A one-way trip measured in thousands of years just for the inbound leg. No human probe has come close to the Oort Cloud. Voyager won the fastest, most distant object ever launched by human civilization, has been traveling since 1977 and currently sits at roughly 160 astronomical units from the Sun. At that rate, it would take approximately 300 years just to reach the inner edge of the Oort Cloud, and roughly 30,000 years to cross it completely. The Oort Cloud is not unreachable the way another galaxy is unreachable. It is unreachable the way the deep ocean floor was unreachable to a sailor in the year 1000, not infinitely far, just far beyond any tool that currently exists. So we do what science does when direct observation fails. We read the evidence, trust the geometry, and accept what the data demands. The solar system is not a disk floating in empty space. It is a disk wrapped inside a sphere so large it stretches nearly 1/4 of the distance to the nearest star. A sphere so cold, so dark, so remote that no human technology has ever touched it, and yet so real that it sends us billion-year-old messengers made of ancient ice, arriving from every direction, on orbits measured in millions of years. The Oort Cloud is not a footnote to the solar system. It is the solar system, in its true and actual scale. But if the Oort Cloud is the outermost boundary of the solar system, that boundary is not standing still. It is hurtling through the galaxy at a speed and angle that most people have never been taught, and the tilt it carries with it makes the words above and below completely meaningless. The most common picture of our place in the Milky Way goes something like this. The solar system is a small dot sitting quietly inside the galactic disk, moving along with everything else in a smooth, parallel path, like a boat gliding flat across the surface of a calm lake. In nearly every popular astronomy illustration ever produced, the solar system appears as a tiny speck nestled obediently inside one of the spiral arms, coplanar with the vast rotating disk, moving in the same direction and on the same level as the stars around it. It looks orderly. It looks peaceful. It looks like we belong exactly where we are, oriented exactly as we should be. That picture is wrong in a way that changes everything. The ecliptic plane of our solar system, the flat disk on which the planets orbit the Sun, is tilted approximately 60 degrees relative to the plane of the Milky Way's galactic disk. 60 degrees, not slightly angled, not a minor lean. More than halfway to perpendicular. We are not gliding flat across the galaxy like a boat on a lake. We are cutting through it at a steep diagonal, like a blade entering water at an angle. The hull tilted hard to one side, the whole vessel carving through the medium at a slant. And we are doing this at a speed that the human brain is genuinely not equipped to process. The solar system is currently moving around the center of the Milky Way at approximately 828,000 kilometers per hour, roughly 230 kilometers per second. To feel what that number actually means, if you could drive a car at that speed, you would circle the entire Earth not once, not 10 times, but 20 full times in a single second. The solar system has been moving at this speed, at this angle, through this galaxy, for the entirety of its 4.6 billion year existence. Every planet, every moon, every comet in the Oort Cloud, every atom in your body, all of it, hurtling through the galaxy at 60 degrees off axis, continuously, without pause. Think of a commercial airplane taking off not straight down the runway, but angled 60 degrees away from the direction of the wind. It still moves forward, it still climbs, but the way it interacts with the air around it, the resistance, the turbulence, the forces acting on every surface is completely different from a clean, aligned takeoff. That is the solar system, not flying clean through the galaxy, cutting through it at a diagonal that reshapes every interaction it has with the material around it. This 60-degree tilt is also what demolishes one of the most instinctive assumptions people carry about space, the idea that up and down means something fixed and real. If the solar system is tilted 60 degrees relative to the galactic disk, then what we call above the solar system, the direction perpendicular to the ecliptic plane, pointing away from the North Pole of Earth's orbit, is not pointing straight out of the galaxy. It is pointing at a 60-degree angle through the galactic disk itself. Above the solar system, in the direction humans have conventionally labeled up, is a region of space inside the galaxy, not outside it. And below is a different region, also inside the galaxy. On the other side of that diagonal path, two astronauts floating in opposite orientations inside the International Space Station. One facing the floor, one facing the ceiling, are in identical physical situations. Neither one is upside down. Neither one is right side up. Those words lose their meaning the moment there is no gravity anchoring a preferred direction. The same principle applies to the solar system inside the galaxy, only at a scale that spans hundreds of light years in every direction. When astronomers say above or below the solar system, they mean one specific thing, the direction perpendicular to the ecliptic plane. That is the only definition that makes geometric sense, and in that direction, both above and below, there are structures that took centuries of observation to begin understanding. Structures that have nothing to do with the flat galactic disk and everything to do with the deep history of the universe itself. There is also a practical irony buried in all of this. If you walked up to an astronomer at a conference and asked a simple question, which direction is the Earth moving right now? In the universe, the honest answer would require a three-dimensional diagram with at minimum 4 separate arrows pointing in different directions simultaneously. One for Earth's rotation, one for Earth's orbit around the Sun, one for the solar system's path around the galactic center, one for the Milky Way's own motion toward the Great Attractor, each arrow pointing a different way, each operating on a completely different timescale. No single sentence captures it. No answer takes less than 10 minutes to give properly. The universe does not do simple directions. And in that tilted, hurtling journey through the galaxy, the solar system is not simply moving in a straight line. It is also oscillating up and down through the galactic plane in a cycle that scientists have only recently begun connecting to something deeply unsettling in Earth's own biological history. One galactic year, the time it takes the solar system to complete one full orbit around the center of the Milky Way, lasts approximately 225 million to 250 million Earth years in its 4.6 billion year lifetime. The solar system has completed somewhere between 18 and 20 full laps around the galaxy. Each one of those laps is not a flat, circular path. Because of that 60-degree tilt between the ecliptic plane and the galactic disk, the solar system does not travel in a clean horizontal loop around the galactic center. Instead, it traces a path that bobs up and down through the galactic midplane, oscillating like a sine wave, dipping below the central plane of the galaxy, rising above it, crossing back through, rising again, in an endless vertical rhythm superimposed on top of the larger orbital motion. The period of that oscillation is approximately 30 million to 35 million years. Every 30 to 35 million years, the solar system crosses through the galactic midplane, the densest, most crowded region of the galactic disk. The amplitude of the oscillation extends roughly 230 light-years above and below the midplane on each side. So the solar system is swinging through a vertical range of nearly 460 light-years total, crossing the most matter-dense region of the galaxy twice per oscillation cycle, continuously for billions of years. Every time the solar system passes through the galactic midplane, it moves through a region with significantly higher concentrations of interstellar matter, molecular clouds, and cosmic radiation than the quieter regions further from the plane. The gravitational environment becomes more complex. The density of material, the heliosphere, must push against increases. The exposure to high-energy cosmic rays, particles traveling at near the speed of light from distant supernovae and other violent sources, goes up. And here is where it stops being abstract. Some researchers have noted a statistical correlation between the approximately 30 million year oscillation cycle and the timing of mass extinction events in Earth's geological and fossil record. The timing of several major extinctions events that wiped out significant percentages of all species on Earth appears to cluster around intervals that roughly match the period at which the solar system crosses through the galactic midplane. The correlation has been examined seriously in peer-reviewed literature. It has not been dismissed. It has also not been confirmed as a direct causal relationship. The mechanisms that would connect galactic position to biological catastrophe on Earth are not yet established with certainty, and the research is ongoing. But the implication is already extraordinary. Our position in the galaxy is not a neutral background condition. It is a variable, one that changes on timescales of tens of millions of years, cycling through environments of varying density and radiation, and potentially leaving marks in the fossil record of life on Earth. Think of a submarine that does not travel in a straight horizontal line, but instead follows a slow, rhythmic rise and fall through the ocean, surfacing periodically into warmer, brighter, more turbulent water, then descending again into cold and dark. Each time it crosses through the boundary layer between deep and shallow, the environment it operates in changes completely. Temperature shifts, pressure changes. The biological communities surrounding it are entirely different. Only in this case. The submarine is the entire solar system. The rise and fall cycle takes 30 million years to complete, and the consequences of crossing the boundary are measured not in discomfort, but in the extinction of species. The solar system has made this crossing dozens of times in its existence. Earth has been along for every single one of them. Life on this planet has survived repeated passages through the most crowded and energetic region of the galactic disk, each one representing a period of elevated environmental stress on a scale no geological force on Earth can replicate. And right now, we are somewhere in the middle of one of those oscillations, not at the midplane, not at the maximum height, somewhere in between, moving, always moving, in a direction and at an angle that most people alive today have never been told about. If our position in the galaxy can influence life on Earth in cycles of 30 million years, what is protecting us during that entire oscillating journey? The answer is a shield with a shape that no one expected, and the only two probes humanity has ever sent past its boundary transmitted data back that completely changed how we understand the word home. When most people think about the edge of the solar system, they think about Neptune, the outermost planet, the last giant. Sitting at roughly 30 astronomical units from the Sun, 1 astronomical unit being approximately 93 million miles, the average distance from Earth to the Sun. 30 of those. That feels far. That feels like a boundary. That feels like the place where the solar system hands off to empty space and the story ends. Some people push it a little further and land on the Kuiper Belt, the broad disk of icy bodies extending from Neptune's orbit out to roughly 50 astronomical units. Pluto lives there. Eris lives there. A whole population of frozen, distant worlds strung across the outer darkness that most people have never heard of. 50 astronomical units. Surely that is where the solar system ends. Somewhere in that 30 to 50 astronomical unit range, the solar system gives way to interstellar space, and everything beyond that point belongs to the void between stars. Wrong. Wrong by a factor so extreme, it does not feel like a correction. It feels like being told the building you thought was 10 stories tall is actually 30,000 stories tall, and the elevator only goes to the second floor. The Oort Cloud does not begin at 30 astronomical units. It does not begin at 50. It does not begin at 100, or 500, or 1,000. The inner edge of the Oort Cloud sits at somewhere between 2,000 and 5,000 astronomical units from the Sun. 2,000. The starting point, not the far edge, not the middle. The absolute nearest boundary of its innermost region is already 66 times farther from the Sun than Neptune. Every diagram you have ever seen of the solar system, every scale model in every science museum, every poster in every classroom, every animation in every documentary, all of it, every planet and moon and asteroid and comet visible to human eyes, represents less than 1.5% of the distance to where the Oort Cloud even begins. And the outer edge, 100,000 astronomical units from the Sun, nearly 1/4 of the total distance to Proxima Centauri, the nearest star to our Sun, which sits at approximately 268,000 astronomical units away. The solar system does not end near the planets. It does not end at the Kuiper Belt. It ends, if the word ends carries any meaning at all in this context, in a vast frozen shell that stretches almost 1/4 of the way to the next star in the galaxy. The solar system and the nearest neighboring star system are not separated by a clean, empty gulf. Their outer gravitational territories nearly overlap. No comparison makes this more viscerally clear than this one. Take the entire planetary solar system from the Sun all the way out to Neptune at 30 astronomical units and shrink it down to the size of a single United States quarter coin, about 1 inch across, sitting in the center of your palm. At that exact same scale, the Oort Cloud surrounding it would extend outward to fill an area the size of a full NFL football stadium. Not the playing field, the entire stadium, the seats, the upper decks, the outer walls, the parking structure surrounding that coin completely from every direction in 3 dimensions, and the coin that single inch of metal representing every planet, every moon, every asteroid, every spacecraft humanity has ever launched, every world humans have ever walked on or photographed or sent a probe to sits alone at the exact center of the stadium floor. Too small to see from the upper deck. That is the true scale of the solar system. The coin is what we were taught. The stadium is what actually exists. Now, a reasonable objection presents itself immediately. No probe has ever reached the Oort Cloud. No telescope has ever produced a direct image of an Oort Cloud object sitting in its natural orbit at tens of thousands of astronomical units. The Voyager probes, the most distant human-made objects ever launched, are currently somewhere around 160 to 130 astronomical units from the Sun, respectively. Still orders of magnitude short of the Oort Cloud's inner boundary. If no instrument has ever seen it, and no probe has ever touched it, how can anyone state with confidence that it exists at all? The answer uses the same logic applied to detecting an active underwater volcano without ever diving to the pressure-crushed seafloor where it burns. You do not need to touch the volcano directly to know it is there. You measure the temperature anomalies in the water column above it. You detect the chemical signatures rising through thousands of feet of ocean. You observe the effects it produces on everything in its vicinity and work backward to the source. The volcano announces its existence through what it does to the environment around it. The Oort Cloud does exactly the same thing. It announces its existence through the long-period comets it sends toward the Sun, objects whose orbital trajectories, when traced backward mathematically, lead to a spherical source distributed at distances of tens of thousands of astronomical units in every direction simultaneously. The geometry does not allow ambiguity. The math has one solution. The Oort Cloud is the basement of the cosmic house, the level you have never visited, the door to which sits 2,000 astronomical units away, requiring 37,000 years of travel at the speed of the fastest vehicle humanity has ever built. You know it exists because things keep falling up from it. Ancient icy objects shake loose from their billion-year orbits and fall inward, growing bright tails as they approach the sun, blazing across Earth's sky as comets and broadcasting their origin coordinates through the mathematics of their own trajectories as clearly as a return address printed on an envelope. But the Oort Cloud is not just a passive boundary sitting quietly at the outermost edge of the solar system, absorbing silence for billions of years. It is the living archive of the solar system's entire formation history, and what placed those primordial fragments there in the first place was a violent series of events so extreme they permanently and irreversibly restructured the architecture of the early solar system itself. 4.6 billion years ago, the same rotating protoplanetary disk that built the planets also produced something else entirely. Alongside the material that would eventually accrete into Mercury, Venus, Earth, Mars, and the giants, the outer cold regions of the disk were generating billions of smaller objects, chunks of rock and ice crystallized at temperatures low enough for water, methane, ammonia, and carbon dioxide to freeze into solid form. These were not failed planets. They were not planets at all. They were the leftover construction material of a solar system, being assembled the unused bricks after the buildings were finished, still lying scattered across the worksite. They did not stay where they formed. In the first tens of millions of years after the solar system's birth, Jupiter and Saturn were already the dominant gravitational forces in the outer solar system. Their combined mass dwarfed everything else beyond the Sun, and their influence reached across enormous distances. When one of those small icy objects drifted into the gravitational territory of Jupiter, the encounter was not subtle. Jupiter's gravity seized it, accelerated it along a sharply curved trajectory, and released it at a velocity far beyond what it arrived with the same mechanism a baseball bat uses, not holding the ball, but transferring kinetic energy into it through the impact and sending it flying in a completely new direction at a completely new speed. The ejected object did not have enough velocity to escape the solar system entirely. The Sun's gravity was still sufficient to hold it, but it was thrown far enough outward to settle into an extremely distant, loosely bound orbit at the very edge of the Sun's gravitational reach, tens of thousands of astronomical units out, moving so slowly at that distance that completing a single orbit around the Sun takes millions of years. This did not happen once. It did not happen thousands of times or even millions of times. It happened billions upon billions of times, continuously, over tens of millions of years. Jupiter and Saturn acting as the solar system's twin gravitational catapults, systematically clearing the middle and outer solar system of loose icy debris and depositing it piece by piece into a vast frozen reservoir at the absolute boundary of solar influence. Every close encounter between an icy body and one of the giants resulted in another ejection, another object flung to the outer darkness, another brick added to what would become the Oort Cloud. The objects resting there today have not been disturbed since the Sun's light, reduced to a brightness barely distinguishable from the surrounding stars at that distance, provides no meaningful heat. No geological processes operate on these isolated chunks of ancient ice and rock. No collisions reshape them. No radiation breaks down their chemistry in any significant way. The icy bodies of the Oort Cloud are preserved in essentially the same chemical state they crystallized into 4.6 billion years ago, sitting at temperatures just a few degrees above absolute zero, frozen in the outer dark, untouched across the entire history of the solar system. When one of these objects is disturbed and falls inward, when it finally reaches the inner solar system after a journey of millions of years, covering 100,000 astronomical units, and the sun's radiation begins to sublimate its surface, converting ice directly to gas for what may be the very first time since the object formed. What gets released is a precise chemical record of the original protoplanetary disk, the exact molecular mixture present in the solar system before any planet finished forming, before any ocean filled, before any geological cycle began churning and transforming and recycling material across billions of years. A long-period comet arriving from the Oort Cloud is not simply a lump of ancient ice. It is a time capsule, the most accurate snapshot available of the raw materials that built every world in this solar system, including the one that produced life. When scientists analyze the spectroscopic signatures in a comet's coma and tail, reading the molecular emissions as the ice sublimates and the gases expand into space, they are doing something extraordinary. They are reading the original recipe, the precise inventory of molecules present in the disk 4.6 billion years ago. Some of those molecules complex organic compounds, amino acid precursors. Water ice are the same classes of molecules found in living cells on Earth today. The implication has been explored seriously in astrobiology for decades. Cometary impacts in Earth's early history may have delivered some of the chemical building blocks that contributed to the emergence of life. The Oort Cloud is not just a gravitational storage locker for ancient debris. It may be the source of some of the raw ingredients that made this planet inhabitable. The numbers describing what the cloud actually contains are staggering on their own terms. Estimates of the total population of objects larger than 1 kilometer in diameter range from several billion at the low end to several trillion at the high end. The total combined mass of all that material adds up to roughly 5 times the mass of Earth, but distributed across a spherical volume of space so incomprehensibly vast that the average density of the cloud is effectively 0. If you could teleport yourself into the middle of the Oort Cloud and look in every direction, the sky would appear completely and utterly empty. Individual objects are separated from one another by tens of millions of kilometers on average. There is nothing to see, nothing to detect without instruments of extraordinary sensitivity, nothing to indicate you are surrounded by trillions of ancient frozen worlds rather than pure vacuum. The Oort Cloud is simultaneously one of the most densely populated structures in the solar system by object count and one of the most invisible by any direct measure, which makes the next question unavoidable. If several trillion objects are sitting in stable, cold, billion-year-old orbits at the outermost edge of the solar system, what is capable of disturbing them? What reaches all the way out to 100,000 astronomical units and nudges something loose from an orbit it has occupied since the solar system was young? Any star that passes close enough, and close enough by the standards of interstellar space, means within a few light years, well short of any direct interaction with the planetary solar system, but near enough that the gravitational gradient of the passing star tugs on the loosely bound outer Oort Cloud objects, tilting their trajectories just fractionally out of stability. That fraction is enough. An object whose orbit was stable for 4 billion years suddenly finds itself on a path that leads inward, falling toward the sun on a journey that will take millions of years to complete and may eventually bring it through the inner solar system, past the planets, past Earth, blazing with a tail of sublimated ancient ice. Stellar flybys of this kind are not rare events. They happen on timescales of millions of years geological instants. By the standards of the solar system's age, the sun has experienced hundreds of them across its lifetime. Each one sends a fresh wave of disturbance rippling through the outer Oort Cloud, loosening new objects from their ancient resting places, dispatching new messengers on million-year journeys toward the inner solar system. But before any of those comets can reach Earth, they must first cross a boundary that sits far closer, a shield that has been quietly deflecting the interstellar environment for the entire history of the solar system. a shield whose shape turned out to be one of the stranger surprises in modern planetary science. Every textbook, every classroom diagram, every science museum exhibit on planetary systems, the heliosphere always looks the same. A perfect sphere with the sun sitting at the dead center, the bubble expanding outward in every direction with identical force and identical distance, clean and symmetrical, like a soap bubble frozen in time. The reasoning behind that image feels airtight. The solar wind, the continuous stream of charged particles the sun fires outward at speeds between 400 and 800 kilometers per second, radiates in every direction simultaneously. Omnidirectional source, omnidirectional result. Why would the bubble be anything other than round? This is one of the most widespread incorrect illustrations in all of popular astronomy. The heliosphere is not a sphere. It is shaped like a distorted teardrop, or more precisely, like the wake a moving boat carves through open water. The front face, pointing in the direction the solar system is traveling, is compressed and blunted by the resistance of the interstellar medium pressing back against it. The rear, the heliotail, stretches out behind for hundreds to potentially thousands of astronomical units, drawn long by the motion, trailing like a comet tail at a scale that dwarfs any comet ever measured. The mechanism is not complicated once you know the solar system is moving. The heliosphere does not sit inside a vacuum. It sits inside the interstellar medium, the thin, continuous mixture of gas and dust, filling the space between stars throughout the galaxy. That medium is not stationary relative to the solar system. The solar system is plowing through it. The front of the heliosphere rams into incoming interstellar material continuously, generating pressure that shoves the boundary inward. The rear faces no equivalent head-on resistance, so the solar wind expands largely unopposed behind, forming that elongated heliotail extending rearward with no clean terminus yet mapped. A candle flame carried quickly through still air does not burn in a sphere. The motion flattens it, pressing the front in, drawing the back out into a teardrop. The heliosphere is that flame. The interstellar medium is the air. The solar system has been moving through that medium for 4.6 billion years, and the heliosphere has been shaped by that motion for every single one of them. NASA's IBEX mission. The Interstellar Boundary Explorer, launched in 2008, spent years mapping the particle and radiation emissions from the heliosphere's outer regions and returned data confirming the asymmetric structure directly. Subsequent observations refine the picture. The shape is not theoretical conjecture. It is measured, documented, real. The textbook sphere was a comfortable simplification that outlasted its usefulness by several decades. Inside that asymmetric shell, the structure runs in distinct layers. Closest to the sun, the solar wind streams outward at full supersonic velocity, its magnetic field threading through the particle flow largely intact. That undisturbed outflow continues until it reaches the termination shock, a boundary where the solar wind abruptly drops from supersonic to subsonic speed. Not gradually. The deceleration happens across a relatively narrow zone, and the physics on either side of it differ sharply. Voyager 1 crossed the termination shock in 2004 at approximately 94 astronomical units from the Sun. Voyager 2 crossed it in 2007 at roughly 84 astronomical units. The different distances on opposite sides of the solar system confirmed that the termination shock itself is not a uniform sphere. It varies in distance depending on the direction measured. Beyond the termination shock lies the heliosheath, a turbulent, compressed region where the slowed solar wind piles up against the resistance of incoming interstellar material. Both Voyager probes spent years transmitting data from inside the heliosheath. The measurements described it as more chaotic and structurally complex than models had predicted. The competing pressures, solar wind pushing out, interstellar medium pushing in, create an active, messy collision zone rather than a clean boundary. The outer edge of the heliosheath is the heliopause, the final line, the place where the solar wind is completely neutralized, its pressure reduced to zero, and on the other side, the interstellar medium flows freely and undisturbed by anything the sun produces. The heliopause sits at approximately 120 astronomical units from the sun on the compressed leading face. On the heliotail side, the boundary extends potentially several hundred astronomical units outward. That asymmetry is not a footnote. It means the heliosphere's shielding is dramatically thicker in some directions than others. The protection is uneven. The shield has a reinforced face and an extended, thinner flank, and Earth, orbiting at 1 astronomical unit, moves through different orientations relative to that asymmetric protection as the solar system travels through the galaxy. You might think a teardrop instead of a sphere. Does the shape really matter in practice? The answer is yes, completely. Because shape determines shielding, a uniform sphere would protect every direction equally. An asymmetric teardrop does not. The degree of protection against galactic cosmic rays. High-energy particles streaming in from distant supernovae and other violent sources throughout the galaxy differs depending on which face of the heliosphere is doing the blocking. The compressed front is thicker, denser, more effective. The elongated tail is thinner and more permeable. That difference is measurable, real and relevant to what penetrates the heliosphere and reaches the inner solar system where Earth orbits. All of this, the compressed leading face, the heliotail, the layered internal structure, the directional asymmetry. We know not only from theory, but from 2 small robots launched in 1977, now traveling alone toward the stars, still transmitting signals back to Earth after nearly 50 years. Voyager 1 crossed the heliopause in August of 2012. Its distance from the sun at that moment, approximately 121 astronomical units. It became the first human-made object in history to enter interstellar space, not planetary space, not the interior of the solar system's magnetic bubble, but the actual medium between stellar systems. The interstellar medium, the material that fills the galaxy between one star and the next. The confirmation required nearly a year of analysis. Scientists needed multiple independent instrument readings to agree simultaneously before the announcement could be made with certainty. Particle densities shifted. Magnetic field orientation changed direction. The ratio of solar particles to interstellar particles inverted abruptly. Every instrument sensitive to the boundary detected it crossing. Voyager 1 had left the sun's domain. Voyager 2 followed in November of 2018, crossing the heliopause at approximately 119 astronomical units from the sun, but on the opposite side of the heliosphere from Voyager 1. That difference mattered enormously. For the first time ever, humanity held 2 simultaneous direct measurements at the solar system's outer boundary, taken from opposite sides at the same time. The comparison revealed something the single probe data alone could never have shown. The heliopause is not symmetric. Crossing conditions on Voyager 2's side differed from those on Voyager 1's side in ways that mapped directly onto the heliosphere's asymmetric shape, slightly thinner on Voyager 2's trajectory, with different plasma densities and magnetic field configurations, confirming 2 genuinely different environments, meeting the same boundary from 2 different angles. Both probes told the same essential story about what lies outside. The interstellar medium is not gentle. Particle density increases sharply beyond the heliopause. Galactic cosmic rays arrive in greater numbers and at higher energies than inside the heliosphere. The heliosphere is not simply a magnetic bubble. It is an active radiation shield, and its effectiveness becomes quantifiable precisely because 2 probes crossed to the unshielded side and sent back the comparison data. Now consider the arithmetic of where these probes actually are. Voyager 1 is currently more than 160 astronomical units from the sun. moving away at approximately 17 kilometers per second. 61,000 kilometers per hour. It has been traveling since September 5th, 1977. Its radio signals take more than 22 hours to reach Earth, traveling at the speed of light. Engineers at NASA's Deep Space Network listen for a transmission weaker than the power output of a refrigerator light bulb, arriving after crossing 160 astronomical units of interstellar space, and they still receive it. But here is where the arithmetic becomes genuinely disorienting. Voyager 1 has crossed the heliopause. By the most intuitive definition, the edge of the sun's direct particle influence it has left the solar system. And yet, by the gravitational definition, it has not left at all. The inner boundary of the Oort Cloud sits at somewhere between 2,000 and 5,000 astronomical units from the sun. Voyager 1 is at 160 astronomical units. At its current speed, reaching the Oort Cloud's inner edge requires approximately 300 more years of continuous flight. Crossing the Oort Cloud completely from its inner boundary to its outer edge at 100,000 astronomical units requires roughly 30,000 years from today. Voyager 1, the fastest and most distant object humanity has ever built, traveling for nearly 50 years without pause, has covered less than 1% of the distance needed to exit the solar system by its true gravitational boundary. The ant has crawled out of the central room. It has passed through the doorway, but the hallway stretching ahead of it runs 30,000 years of walking before the building's exterior wall comes into view. Voyager 1 travels at 61,000 kilometers per hour. It still needs 30,000 years to escape the solar system. If you had launched it at the moment modern Homo sapiens first appeared in Europe, you would still be waiting for it to arrive. But as enormous as the heliosphere is, it does not operate in a vacuum. It is actively fighting, at every moment, against a cloud of material surrounding the solar system. From every direction, a cloud the solar system swam into, somewhere between 40,000 and 100,000 years ago, and has not yet crossed out of. Interstellar space, in the popular imagination, is empty, completely, perfectly empty. The void between stars is the void nothing but darkness, vacuum, the absence of everything. Between the Sun and Proxima Centauri sits 4.24 light-years of absolute nothing. That is why it is called space. Space, by definition, is the space between things. The things are the stars. Between the stars there is nothing. This is wrong in a way that turns out to matter enormously for the story of where the solar system actually is right now. Interstellar space is not empty. It never was. The entire galaxy is threaded through with the interstellar medium, a continuous, galaxy-wide mixture of gas and dust so diffuse it registers as near vacuum by any engineering standard, but so vast in total volume that its cumulative mass is staggering. The gas is mostly hydrogen and helium, the simplest atoms in existence, with traces of heavier elements seeded by billions of years of stellar deaths. The dust is grains of silicate, carbon compounds, and frozen molecules, ground to microscopic sizes by billions of collisions over billions of years. It is thin. It is cold in most places, but it is everywhere, filling every cubic centimeter of the space between stars throughout the entire galaxy, unbroken. And right now, the solar system is not traveling through a generic, average patch of that medium. It is traveling through a specific named structure, a region of the interstellar medium with measurable, documented properties distinct from its surroundings. Astronomers call it the local interstellar cloud. Most scientific literature abbreviates it to LIC informally, and this name is real and used in published papers. It is called the fluff. The fluff. That is the official informal designation for the cloud currently surrounding our entire solar system. The LIC is a region of slightly elevated gas density compared to the surrounding interstellar medium, roughly 30 light-years across. The solar system entered it somewhere between 40,000 and 150,000 years ago, meaning the entry happened during the age of anatomically modern Homo sapiens, not in deep geological prehistory, not in the era of dinosaurs, somewhere in the period when modern humans were already walking the Earth, making tools, crossing continents. The solar system quietly drifted into a new neighborhood, and nobody noticed because there was no way to notice. The properties of the LIC, measured through decades of ultraviolet spectroscopy and particle detection, are specific. Density approximately 0.26 atoms per cubic centimeter. That sounds negligible. For comparison, the average density of the interstellar medium generally runs around 0.1 atoms per cubic centimeter. So the LIC is roughly 2.5 times denser than the galactic average, still essentially nothing by any physical standard you can hold in your hand. But enough. Enough that the heliosphere has to actively push against it, continuously, to maintain its boundary. The termination shock, the Helios heath, the heliopause, every layer of the heliosphere's internal structure exists partly because the LIC is pressing on the outside. Temperature of the LIC approximately 6,000 to 7,000 Kelvin. That surprises people. A sparse cloud of gas drifting through interstellar space conjures images of something cold, quiet, nearly inert. 6,000 to 7,000 Kelvin is hotter than the visible surface of some stars. The heat comes from the same processes that ionize the gas ultraviolet radiation from nearby hot stars. The cumulative energy input from the violent history of the surrounding region. The LIC is not cold. It is a hot, thin, continuously flowing medium, and the solar system is swimming through it at a relative velocity of approximately 26 kilometers per second. That relative velocity, 26 kilometers per second, is what the heliosphere feels as the interstellar wind. The LIC is not stationary relative to the solar system. It flows past the heliosphere the way a river flows past a boulder sitting in its current. The boulder deflects the water. The heliosphere deflects the LIC, but the deflection costs energy, and the shape of the heliosphere, compressed on the leading face, drawn out in the heliotail, is the direct physical consequence of that cost. Every asymmetric feature of the heliosphere discussed in the previous section traces back, ultimately, to the LIC pressing against it at 26 kilometers per second, every second, for tens of thousands of years. Now the chain collapse question. If the solar system entered the LIC between 40,000 and 150,000 years ago, and the LIC is approximately 30 light-years across, how much farther does the solar system have to travel before it exits? And what happens when it does? Current estimates place the exit somewhere between 10,000 and 20,000 years from now. 10,000 to 20,000 years. In the context of the solar system's 4.6 billion year history, that is an eye blink less than 0.1% of the solar system's total age. In the context of human civilization, it is a span roughly comparable to the entire recorded history of organized human societies from the first writing systems to the present day. The solar system will leave the local interstellar cloud within a time frame that human civilization might plausibly survive to witness. When it does exit, the consequences for the heliosphere are not trivial. The region beyond the LIC in the direction the solar system is currently heading is significantly less dense than the LIC itself. Lower external pressure means less compression. The heliosphere, freed from the specific resistance of the LIC, is expected to expand. The termination shock moves outward. The heliopause extends. The entire protective bubble swells, and a larger, differently shaped heliosphere means a different flux of galactic cosmic rays reaching the inner solar system. More shielding in some configurations, less in others, depending on geometry. The biological and atmospheric consequences of that shift are not yet modeled in enough detail to make confident predictions, but the shift itself is coming. On a timescale that is not geological, it is almost human. Scientists name this cloud the fluff, not the grand shield, not the stellar fortress, not the interstellar barrier. The fluff. It is reasonable evidence that scientists are excellent at measuring things and genuinely terrible at naming them. The cloud surrounding our entire solar system, the medium the heliosphere has been fighting against for tens of thousands of years. The structure that will exit our path within a time span comparable to human civilization is called the fluff. But the LIC is only the current stop on a much longer journey, and the larger picture surrounding it reveals that the solar system is drifting inside an enormous cosmic wound, carved out by explosions at a scale that is nearly impossible to imagine. The local interstellar cloud does not exist in isolation. It never did. The LIC sits inside a larger structure called the G cloud, another named region of the local interstellar medium, with its own distinct density and temperature profile, adjacent to the LIC and partially overlapping its boundary. The G cloud is where the solar system is likely heading after it exits the LIC, moving from one named cloud into the next, the way a ship moves from one weather system into another, neither transition visible in real time. Both transitions measurable only through the instruments that sample the medium as the solar system passes through it. But the G cloud is not the enclosing structure either. Both the LIC and the G cloud, along with several other named local clouds in the solar neighborhood, sit inside something vastly larger. The region immediately surrounding the LIC is called the hot local bubble, and this is where the scale jumps by an order of magnitude that the previous structures did not prepare you for. The hot local bubble is a region of extraordinarily low-density, high-temperature plasma extending hundreds of light years in multiple directions from the solar system. The gas density inside it is far lower than even the already thin interstellar medium of the LIC, approximately 1/10 to 1/100th the density of the LIC in the hottest central regions. The temperature, by contrast, is not 6,000 to 7,000 Kelvin like the LIC. The hot local bubble plasma reaches temperatures of approximately 1 million Kelvin. 1 million. The contrast between the LIC, relatively dense, 6,000 Kelvin, flowing at 26 kilometers per second, and the surrounding hot local bubble, almost empty. 1 million Kelvin. A different physical regime entirely is not subtle. The boundary between them is a real interface where conditions change sharply. And when the heliosphere exits the LIC and encounters the hot local bubble's environment directly, its response will be unlike anything it has experienced for the last 100,000 years. The shape of the heliosphere, as it crosses that boundary, is something scientists have modeled, but not yet directly observed. Lower external pressure, dramatically thinner medium, temperatures that ionize the surrounding gas into a state of plasma rather than neutral hydrogen. All of it changes the balance of forces the heliosphere maintains. The bubble expands, perhaps dramatically. By how much? In what time frame? With what measurable effects on cosmic ray penetration into the inner solar system? Those questions sit at the frontier of current research. The honest answer is that the details are not fully known. The direction of change is known. The magnitude is not. Now set aside the LIC and the G cloud and the hot local bubble individually and look at the structure that contains all of them. The LIC, the G cloud, the hot local bubble. They are rooms inside a building. The building is the local bubble. The local bubble is a cavity in the galactic disk, roughly ellipsoidal in shape, approximately 1,000 light-years long and 700 light-years wide. It is not a subtle feature. It is a massive hollowed-out region of the galaxy's disk, carved from the surrounding denser interstellar medium by a prolonged campaign of destruction. Inside it, the gas density is far lower than the galactic average. The temperature is far higher. The entire structure represents a volume of the galaxy that was systematically stripped of its normal interstellar material by repeated catastrophic energy releases over millions of years. The local bubble did not form naturally, in the sense of forming through the slow accumulation of ordinary processes. It was blasted into existence. The current best estimate, supported by detailed three-dimensional mapping of the surrounding dust and gas, published by Catherine Zucker and collaborators in Nature in 2022, attributes the local bubble to at least 15 separate supernova explosions occurring over the last 10 million to 20 million years. Each supernova detonated a shockwave into the surrounding interstellar medium, a spherical pulse of energy expanding at thousands of kilometers per second, pushing gas and dust outward, compressing it at the leading edge of the shockwave, hollowing out the interior behind it. 15 of those events staggered across millions of years, each one adding to the growing cavity, each one sweeping more material to the outer walls. The evidence for those explosions does not live only in telescopic observations of the surrounding medium. Part of it lives on Earth, specifically on the ocean floor. That connection bridges two seemingly unrelated fields, deep-sea sediment chemistry and astrophysics, in a way that, when first proposed, many researchers found difficult to accept. If the physical evidence of those galactic explosions is sitting right now at the bottom of Earth's oceans, that means cosmic events hundreds of light years away left direct physical traces on the planet we are living on. The answer is yes. And when scientists first found that evidence on the ocean floor, it took them years to believe their own data. When people think about evidence for cosmic events, they think about telescopes, satellites, orbital observatories perched above the atmosphere, scanning the sky in wavelengths the human eye cannot detect. The evidence in that mental model lives up there in space, far away, accessible only through instruments of extraordinary sophistication pointed outward into the dark. Nobody thinks about drilling into ocean mud. In 1999, a research team led by Dr. Klaus Knie at the Technical University of Munich was doing exactly that, analyzing deep-sea sediment cores, layers of ocean floor material deposited over millions of years, each millimeter of compressed mud representing thousands of years of slow accumulation. Buried inside those layers, at a specific depth corresponding to approximately 2 to 3 million years ago, they found something that had no business being there: an anomalous concentration of iron-60, written in scientific notation as 60 AFE, a radioactive isotope of iron that does not occur naturally in any significant quantity on Earth or in the solar system's ordinary inventory of materials. Iron-60 is not primordial. It cannot be produced by geological processes, by cosmic ray interactions with surface rocks, or by any mechanism operating inside the solar system under normal conditions. There is exactly one known astrophysical process capable of producing it in quantity: a supernova explosion. When a massive star exhausts its fuel and detonates, the violent nuclear reactions in its collapsing core synthesize heavy isotopes that stable stellar fusion cannot produce, and iron-60 is among them, ejected into the surrounding space in the explosion's ejecta at enormous velocities. Finding iron-60 in ocean sediment meant one thing: a supernova had gone off close enough to the solar system that its ejecta penetrated the heliosphere, traveled through interplanetary space, reached Earth, and settled into the ocean floor. The concentration spike in the sediment layer was not noise. It was a timestamp, a chemical record of a specific cosmic event, preserved in the mud at the bottom of the sea, waiting 2 to 3 million years for someone to come looking. The mechanism is precise. A supernova occurring within approximately 300 light-years of the solar system produces a shock wave and an ejecta cloud containing iron-60 and other exotic isotopes. If the explosion is close enough, the ejecta eventually reaches the heliopause, the outer boundary of the heliosphere, and some fraction of it penetrates into the inner solar system. The particles then behave like any other interplanetary dust. They drift inward under the influence of radiation pressure and gravity, some fraction of them settling onto planetary surfaces over timescales of thousands to tens of thousands of years. On Earth, the ocean floor captures this material in its sediment record with extraordinary fidelity, layering it chronologically like pages in a book, each page representing a few thousand years of cosmic history. Iron-60 has a half-life of 2.6 million years. That number is critical to the interpretation in two distinct ways. Long enough that iron-60 produced by a supernova 2 to 3 million years ago still exists in measurable quantities today. The radioactive decay has not yet erased it completely. Short enough that any iron-60 present in those sediment layers cannot be primordial material left over from the solar system's formation. 4.6 billion years ago, that ancient iron-60 would have decayed through more than 1,000 half-lives and would be entirely gone. The only possible source for iron-60 still detectable in 2 to 3 million year old sediment is a supernova that exploded 2 to 3 million years ago. The chemistry is an airtight argument. The 2 to 3 million year signal found by Ni's team aligned with something else, the estimated timing of the solar system's passage through the dense outer shell of the local bubble. The compressed wall of gas and dust pushed outward by the same supernova sequence that carved the bubble. Entering that shell meant entering a region where supernova remnants and their chemical products were concentrated. The iron-60 in the sediment was not from a random distant explosion. It was from the same campaign of destruction that created the cavity the solar system now lives inside. The story did not end with Ni's team. In 2016, a research group led by Anton Wallner published a significantly expanded study in the journal Nature. Wallner's team analyzed sediment cores from multiple locations across different ocean basins, not just one site, but a geographically distributed sample set designed to eliminate any possibility that the iron-60 signal was a local contamination artifact. The results confirmed and extended the original finding. Iron-60 anomalies appeared in sediment layers corresponding to two separate time windows approximately 2 to 3 million years ago and approximately 6 to 7 million years ago. Two distinct pulses, two separate supernova events, or clusters of events, each one leaving its radioactive fingerprint in the ocean floor of a planet orbiting a star hundreds of light years away. The implication does not stay comfortable if you follow it to its logical end. Earth directly absorbed radioactive material from supernova explosions. The question that follows is unavoidable. Did that exposure affect anything life on Earth 2 to 3 million years ago? Was already complex early hominids were walking the African savanna. Marine ecosystems had their modern general structure. Land ecosystems were established. A pulse of iron-60 reaching Earth also means a pulse of the broader supernova ejecta and elevated cosmic ray flux that accompanies it. Whether that elevated radiation had measurable biological consequences is a question researchers have raised seriously. No definitive causal link between the iron-60 pulses and specific extinction or evolutionary events has been confirmed. But the exposure was real, documented, physical, not theoretical. It turns out that the evidence for one of the most important astrophysical discoveries of the 21st century lives at the bottom of the sea, not on a mountaintop observatory, not on an orbiting satellite, in ocean mud. The universe hides its evidence in the strangest places. And if supernovae left their fingerprints in the ocean sediment, the bubble those same explosions carved must operate at a scale that is nearly impossible to picture, along with what is happening on its walls right now. The local bubble is a cavity in the galactic disk, ellipsoidal in shape, approximately 1,000 light-years long and roughly 700 light-years wide. Not a small feature, not a subtle fluctuation in interstellar density. A hollowed-out chamber in the galaxy itself, a region where the ordinary interstellar medium has been systematically evacuated, leaving behind a volume of extremely hot, extremely low-density plasma surrounded by a compressed shell of gas and dust at its outer boundary. It was created by at least 15 separate supernova explosions over the last 10 million to 20 million years. Each detonation sent a shockwave expanding outward at thousands of kilometers per second, sweeping gas and dust ahead of it like a demolition charge clearing a room, compressing the swept material into a thickening shell at the leading edge of the blast, hollowing out the interior behind it. 15 of those events spread across millions of years, each one reinforcing and expanding the cavity left by the ones before. The result is the structure the solar system now occupies, a bubble blown by the deaths of massive stars, its walls built from the material those deaths displaced. A 2022 study by Catherine Zucker and collaborators, published in Nature, mapped the three-dimensional distribution of star-forming regions within 500 light-years of the Sun with a precision that had not been possible before. The result was striking. Virtually every young star-forming region in the solar neighborhood, Perseus, Taurus, Ophiuchus, Chamaeleon, and several others, sits not randomly distributed through local space, but specifically on the surface of the local bubble, not inside it, not outside it, on it, distributed across the compressed shell at the outer wall, like material clinging to the skin of a soap bubble, rather than floating in the air inside or outside the film. The reason is physical and direct. The outer shell of the local bubble is where the supernova shockwaves deposited the material they swept up. Over millions of years, that compressed shell accumulated enough gas and dust that gravitational instabilities began to develop within it, regions where density exceeded the threshold for self-gravitating collapse. New stars began forming in the compressed debris of old stellar deaths. The wall of the local bubble is, right now, an active stellar nursery. The destruction of stars that happened 10 million to 20 million years ago is directly and causally producing new stars today. On the outer surface of the wound, those deaths carved Perseus, Taurus, Ophiuchus, Chamaeleon regions astronomers have studied for decades as textbook examples of active star formation are all sitting on the wall of a bubble blown by supernovae. They are not forming stars because of some independent local process. They are forming stars because the shockwaves from stellar explosions millions of years ago compressed the material that is now collapsing into new suns. Death begetting birth at a scale spanning hundreds of light years, on a timeline spanning millions of years. The solar system itself was not always inside the local bubble. It entered approximately 5 million years ago, as its long orbit around the galactic center carried it through the outer shell and into the evacuated interior. Before that entry, the solar system moved through denser interstellar medium. The heliosphere was more compressed, pushed harder from outside, its boundaries sitting closer to the Sun. After entering the bubble, the external pressure dropped. The heliosphere expanded. The flux of galactic cosmic rays reaching the inner solar system changed. Earth's exposure to the high-energy particle environment of the galaxy shifted in ways that are still being studied, with possible connections to climate and atmospheric chemistry that remain active research questions. 5 million years ago. That was not long before early hominids began their divergence from other great apes. Whether the timing is coincidental or meaningful is an open question, and the honest answer is that no confirmed causal link exists. But the solar system's entry into the local bubble changed its environment in real, physical, measurable ways. And those changes were ongoing through the period when life on Earth was undergoing some of its most consequential evolutionary transitions. The correlation is noted. The mechanism, if any, is not established. What is established is the picture of where we are, living inside a cavity blasted into the galaxy by at least 15 supernova explosions. Drifting through the fluff, a warm, slightly dense cloud inside that cavity. The outer walls of our bubble actively generating new stars from the compressed remnants of the explosions that created it. Radioactive isotopes from those same explosions sitting in layers of ocean sediment on our planet right now. Measurable, datable, real. We are not in a quiet corner of the galaxy. We never were. On those walls, stars are forming. Some of them are forming planetary systems, disks of gas and dust coalescing around new suns. The same process that built the solar system 4.6 billion years ago, playing out again in compressed supernova debris on the outer surface of the bubble we call home. Some of those forming planetary systems may eventually produce worlds. Some of those worlds, given enough time, may produce conditions favorable to chemistry complex enough to matter. We are living inside the ruins of explosions that may be seeding the next chapter of the galaxy's inhabited history. The destruction of our cosmic ancestors may be directly building the birthplaces of whatever comes after us. But everything described so far, the heliosphere, the LIC, the local bubble, still sits inside the disk of the Milky Way. Step outside that disk, look above and below the galaxy, and there is a structure older than anything we have discussed yet. The Milky Way, in the standard popular image, is a flat spiral disk, 100,000 light-years across, a few thousand light-years thick, arms of stars and gas curling outward from a central bulge. Everything that matters arranged in that single rotating plane. Stars live in the disk. Planets form in the disk. Gas clouds collapse into new stars in the disk. The disk is where the action is. Above and below it in the popular imagination, there is simply darkness, empty space, nothing worth mentioning. That picture is wrong in a direction most people have never thought to look. Above and below the galactic disk, extending outward in every direction from the plane of the Milky Way, sits the galactic halo, a vast, roughly spherical structure enveloping the entire disk, stretching at least 100,000 light-years in every direction from the galactic center. Not a thin shell. A full three-dimensional sphere of space surrounding the flat disk, the way the white of an egg surrounds the yolk. Only in this case, the white extends outward as far as the yolk is wide. The Milky Way is not just a disk. It is a disk embedded inside a sphere, and the sphere is enormous. The galactic halo is not empty. It contains three things: hot ionized gas, diffuse and ancient, threading through the halo volume at temperatures of millions of Kelvin, approximately 150 to 160 confirmed globular clusters, dense, ancient, self-contained collections of stars numbering from hundreds of thousands to several million each, scattered across the halo in orbits that carry them above and below the galactic plane in long, elliptical loops. And something else. Something that makes up the overwhelming majority of the halo's total mass. Something that does not emit light, does not reflect light, has never been directly detected by any instrument ever built, but whose presence is written into the motion of every star in the galaxy. The globular clusters deserve to be understood for what they actually are, not just described as old star clusters and moved past. The Milky Way's confirmed globular clusters number between 150 and 160. Each one is a gravitationally bound sphere of stars not spread across light years like the general stellar population of the disk, but packed into a volume typically between 100 and 300 light years across, with stellar densities at the core that can be thousands of times higher than the solar neighborhood. From inside one, the night sky would be ablaze. Thousands of stars visible to the naked eye, no darkness between them at the galactic core. just a continuous glow of ancient light from every direction. Their ages range from approximately 11 billion to 13 billion years. The universe itself is approximately 13.8 billion years old. These clusters formed when the universe was between roughly 800 million and 2.8 billion years old, before the Milky Way's disk had settled into its current spiral structure. When the galaxy was still a young, chaotic, irregularly shaped system in the process of assembling itself from smaller merging structures. The globular clusters formed in that primordial environment from the first generations of stars, and they have been orbiting the galaxy in the halo ever since. 11 to 13 billion years of continuous existence, through the entire formation of the galactic disk, through the birth of the Sun, 4.6 billion years ago, through the entire history of life on Earth. These clusters were already ancient when the solar system formed. They were already middle-aged when the first multicellular organisms appeared in Earth's oceans. Each globular cluster is a snapshot, a preserved sample of the conditions present in the early universe. The chemical composition of their stars reflects the elemental abundances of the cosmos. Before billions of years of stellar nucleosynthesis had enriched the interstellar medium with heavier elements, they are living fossils of a younger, simpler universe. When astronomers study globular clusters, they are reading a record that no other structure in the galaxy can provide a direct window into the physical conditions of the cosmos closer to the Big Bang than anything in the galactic disk has preserved. Now the objection worth confronting. The stars in globular clusters are old 11 to 13 billion years. The Sun is 4.6 billion years old, and life appeared on Earth within roughly a billion years of the Sun's formation. If life can emerge around a star 4.6 billion years old, then stars 11 to 13 billion years old have had 2 to 3 times as long for life to develop around them. Globular clusters contain hundreds of thousands to millions of stars each. 150 to 160 clusters orbit the Milky Way's halo. The arithmetic of possible worlds is staggering. There are genuine complications. Early generation stars in globular clusters are metal poor. They formed before supernova cycles had distributed sufficient quantities of heavier elements through the interstellar medium. Planet formation requires heavier elements. Rocky planets need silicon, iron, magnesium, oxygen in useful proportions. The oldest globular cluster stars may not have had the raw materials available to build Earth-like worlds. More recent research suggests that some globular clusters, particularly the more chemically enriched ones, may not exclude rocky planet formation as cleanly as the simple metal poor argument implies. The question is genuinely open. But here is the perspective that lands differently once you sit with it. If something is living in a globular cluster in the galactic halo and looking outward toward the Sun, they would see us as newcomers. The Sun moved into this neighborhood 4.6 billion years ago. Their neighbors have been here for 13 billion years. By that accounting, we are the new arrivals. Whatever has had 13 billion years to develop around those ancient stars has had a head start measured in billions of years on anything that has ever existed on Earth. And the galactic halo does not only contain the light of ancient stars, most of its mass is something completely invisible, something that does not emit light, does not reflect light, and we still do not know what it actually is. The first serious indication that something was wrong with the accounting came from rotation curves. Stars orbit the center of the Milky Way, the same way planets orbit the Sun pulled inward by gravity, moving fast enough in their orbital path to avoid falling in. Basic orbital mechanics, the same physics that governs everything from Earth's orbit to a satellite in low orbit, predicts a specific relationship between a star's distance from the galactic center and its orbital speed. Stars closer to the center, where most of the visible mass is concentrated, should orbit fast. Stars farther out, where the gravitational pull is weaker and the mass enclosed within their orbits is less, should orbit progressively slower. The The relationship is called a Keplerian rotation curve, named after Johannes Kepler, who worked out the same relationship for planets around the Sun 4 centuries ago. When astronomers actually measured how fast stars at different distances from the galactic center are moving, the observed rotation curve did not drop off the way Kepler's law demands. Stars at the outer edges of the Milky Way, thousands of light years beyond the bulk of the visible disk, are moving just as fast as stars much closer in some cases, faster. By the physics of visible mass alone, those outer stars should have been flung away from the galaxy long ago. They are moving at speeds that the gravitational pull of all observed stars, gas and dust cannot account for. The galaxy should be flying apart. It is not. The only explanation that survives scrutiny is additional mass, invisible mass. Mass distributed throughout the galactic halo in quantities large enough to supply the gravitational force the visible matter cannot. This is dark matter, not a poetic name for mysterious unknowns, but a technical designation for a real component of the galaxy whose gravitational effects are measured, reproducible, and written into the orbital dynamics of every star in the Milky Way. The estimated proportion is not a small correction. Dark matter accounts for approximately 85% of the total mass of the Milky Way. Everything else, every star, every planet, every gas cloud, every nebula, every grain of interstellar dust, every black hole, every neutron star, everything that has ever been observed, photographed, measured, or theorized about in the visible universe constitutes the remaining 15%. Let that settle. 85% of the galaxy is made of something we cannot see, cannot touch, cannot detect directly with any instrument currently in existence, and cannot identify from first principles. We do not know what it is made of. We do not know what particle carries it, if it is a particle at all. We know it has mass, because mass is gravity, and the gravitational effects of dark matter are written into the rotation of the galaxy with a precision that leaves no room for the alternative. But beyond that, the composition, the physics, the fundamental nature of the thing remains one of the deepest unsolved problems in all of science. The full weight of that fact deserves a moment. Every telescope ever built, from Galileo's first glass lens pointed at Jupiter's moons in 1609, to the Hubble Space Telescope, to the James Webb Space Telescope with its gold-plated mirrors unfolded in the cold darkness of space, every instrument, every observation, every image, every data set accumulated across 4 centuries of modern astronomy has been studying 15% of the galaxy. The science has been extraordinary, transformative, genuinely one of the greatest intellectual achievements in human history. And it has been done while looking at 15% of what is actually there. Think of studying a building of vast, intricate structure, every room connected to every other through a system of load-bearing relationships you are trying to understand. You can see the painted walls. You can measure the rooms. You can describe the layout, catalog the furniture, map every visible surface in extraordinary detail. But 85% of the building, the steel frame, the foundation, the embedded electrical systems, the structural elements that actually hold the thing upright, is invisible to every instrument you have. You are describing the interior decoration of a building whose architecture you cannot see. And that invisible architecture is precisely what is preventing the building from collapsing. If the Milky Way lost its dark matter halo, the disk would not persist in its current form. The gravitational scaffolding holding the spiral structure together, keeping the outer stars in orbit, maintaining the overall mass distribution that shapes the galactic rotation, would vanish, and the disk would begin dispersing on timescales astronomically short by galactic standards. Dark matter is not a mysterious extra. It is the skeleton. The visible galaxy is the skin. Hundreds of years of human astronomy have been studying the galaxy while only seeing 15% of it. What changes in our understanding of the universe if we ever comprehend the 85% that remains? Dark matter is something physicists are absolutely certain exists. Have no idea what it is, cannot see, cannot touch, cannot measure directly, and which makes up 85% of the galaxy's mass in any other field. Saying, "I am certain it exists, but have no idea what it is," would be considered an unconvincing position. In astrophysics, it is the scientific consensus. And this is where all those layers, the Oort cloud, the heliosphere, the local bubble, the galactic halo, dark matter converge into one single largest question amid all that cosmic chaos and violence. How did a small rocky planet become the place where life took hold? Pull back from everything. Let the full picture come into focus at once. Start at the center and move outward. The ecliptic plane, the flat disk on which the planets orbit the sun, the image from every textbook, the plastic model hanging from the classroom ceiling. That is where the story began. Then outward past Neptune, past the Kuiper Belt, into the vast frozen silence of the Oort cloud, a spherical shell of billions to trillions of ancient icy bodies, extending 100,000 astronomical units in every direction. Preserving the original chemistry of the solar system's formation in cold storage for 4.6 billion years, past the Oort cloud's outer boundary, across the gradient where the sun's gravity finally releases its hold, into the heliosphere, that asymmetric, teardrop-shaped magnetic bubble compressed on its leading face, drawn out in a long heliotail behind, actively fighting the interstellar medium at every moment to maintain the boundary that shields the inner solar system from the raw particle environment of the galaxy. Then through the heliopause, into the local interstellar cloud, the fluff warm, slightly dense, flowing past the heliosphere at 26 kilometers per second. A cloud the solar system entered between 40,000 and 150,000 years ago and will exit within the next 10,000 to 20,000 years. Beyond the LIC, the hot local bubble, a vast million Kelvin plasma region of dramatically lower density surrounding the cloud, and containing all of it, the local bubble itself a 1,000 light-year cavity blasted into the galactic disk by at least 15 supernova explosions over the last 10 million to 20 million years, its compressed outer wall currently generating new stars in Perseus, Taurus, Ophiuchus, and Chameleon. Then the galactic disk itself. The full spiral structure, 100,000 light-years across. And enclosing everything the galactic halo, a sphere extending at least 100,000 light-years in every direction. Populated by 150 to 160 ancient globular clusters and pervaded by the invisible gravitational architecture of dark matter that constitutes 85% of the galaxy's total mass. 7 layers, each one a different environment, each one with its own history of violence, its own record of catastrophic events, its own ongoing interactions with the layers surrounding it, interactions we have only begun to map and measure and understand in the last few decades of science. None of those layers is passive. None of them sits quietly while the others operate independently. The supernova explosions that carved the local bubble sent shockwaves outward that compressed the interstellar medium into the wall where new stars are forming today. But they also sent iron 60 raining down through the heliosphere onto the ocean floor of Earth. The oscillation of the solar system through the galactic midplane changes the density of the interstellar environment. The heliosphere must navigate, which changes the heliosphere's size and shape, which changes the flux of cosmic rays reaching Earth's atmosphere. The dark matter halo's gravitational structure shapes the orbits of globular clusters above and below the disk. The local interstellar cloud pressing against the heliosphere at 26 kilometers per second determines exactly where the termination shock sits and how much of the inner solar system the heliosphere can effectively shield. Pull on any one layer and the others respond. The system is not a stack of independent shells. It is an integrated, dynamic, continuously evolving structure, and life on Earth has been embedded inside it for the entire duration of its existence. Life on Earth is not the product of a peaceful, isolated environment. That framing has always been wrong, and the journey through these layers makes it impossible to maintain. Life is the product of the full cosmic history of every single one of those layers assembled, shaped, periodically disrupted, and ultimately enabled by processes operating at scales from the local to the galactic, across timescales from millions to billions of years. The carbon in your body, in your DNA, your proteins, your cell membranes, the structural backbone of every organic molecule that makes you function, was synthesized in the cores of stars that died billions of years before the sun formed. Those stars fused hydrogen into helium, helium into carbon, carbon into heavier elements in successive fusion shells, until the core collapsed and the supernova scattered everything outward into the interstellar medium of the early galaxy. That carbon drifted through the interstellar medium for hundreds of millions of years before the molecular cloud that would become the solar system began to collapse. It then became part of the protoplanetary disk, the same rotating disk that formed the planets, including Earth. Over billions of years of geological and biological processing on this planet, that carbon cycled through rock, ocean, atmosphere, and eventually into the chemistry of living cells. The carbon in your body is stellar ash that has been recycled through at least one prior generation of stars, scattered by supernova, reassembled by gravity, and processed by 4.6 billion years of planetary and biological chemistry. The iron in your blood, the iron in hemoglobin that carries oxygen through your body right now, follows a similar path, but with an additional chapter. Some of that iron may have been synthesized not in the core collapse of a single massive star, but in the collision of two neutron stars, a neutron-star merger, one of the most violent events in the observable universe, capable of producing heavy elements like iron, gold, and platinum in quantities that stellar fusion alone cannot match. Those neutron-star mergers happened billions of years before the solar system formed. The iron they produced entered the interstellar medium, was incorporated into the protoplanetary disk, accreted into the rocky body that became Earth, and eventually found its way into the biological machinery of living organisms. The same category of supernova events that left iron-60 in the ocean sediment layers 2 to 3 million years ago may be distantly related to the processes that seeded the protoplanetary disk with the iron that runs through your veins today. We are not observers standing outside the universe, looking in at cosmic processes from a safe remove. That is the deepest misconception the standard model of science communication perpetuates. The boundary between you and the universe is not the surface of your skin. Every atom in your body has a cosmic biography spanning billions of years and hundreds of light years of travel. You are not in the universe. You are a local, temporary, extraordinarily complex arrangement of material that the universe has been processing for 13.8 billion years. Return then to the original question. What exists above and below our solar system? Not empty space, not a hard boundary where the solar system ends and the void begins. What exists above and below in every direction, at every scale, is a continuous sequence of historical layers. 4.6 billion years of preserved primordial ice in the Oort Cloud. The ash of dead stars compressed into the wall of the local bubble, collapsing now into new suns, the oldest surviving structures in the galaxy, orbiting in the halo above and below the disk. Their light a direct transmission from the universe's first billion years, and threaded through all of it, invisible and dominant, the dark matter that provides the gravitational framework without which none of the visible structure could hold its shape. Every layer connects directly to us, not metaphorically, physically, chemically, causally. If every atom in your body was once part of a star, was once raw material in a protoplanetary disk, was once ejected by a supernova, Then where, exactly, does the boundary between you and the universe actually lie? The scientific answer to the question, who am I, turns out not to be philosophy. It is astrophysics. And that answer is approximately 13.8 billion years long and involves at least 15 supernova explosions. But understanding all of this is not the end of the question. It is only where the question actually begins. The journey from the ecliptic plane to the galactic halo is not a list of cosmic facts. It is a map of where we actually exist in reality, drawn at every scale simultaneously. From the frozen primordial ice, 4.6 billion years old, drifting in the Oort Cloud, to the ancient globular clusters orbiting silently in the halo above and below the galactic disk. Each layer is not just a location. It is a record, a physical archive of everything that had to happen: every stellar death, every supernova shockwave, every gravitational slingshot, every billion-year oscillation through the galactic midplane for the conditions to exist that allow life to sit here, right now, asking questions about all of it. And the questions are far from closed. Dark matter constitutes 85% of the galaxy's mass, and we do not know what it is. Not approximately, not in broad strokes. We do not know what particle carries it, whether it is a particle at all, or what physics governs its behavior beyond the gravitational effects we measure indirectly through stellar motion. The Oort Cloud has never been directly observed. Its existence is inferred entirely from the orbital mathematics of long-period comets, a conclusion so logically airtight that the cloud is accepted as real, despite no instrument ever producing a direct image of a single object sitting in its natural orbit at 50,000 astronomical units. The proposed connection between the solar system's 30 million year galactic oscillation and the timing of mass extinction events on Earth remains statistically suggestive and causally unconfirmed. These gaps are not failures. They are not embarrassments. They are the most honest thing. Science produces a precise map of the boundary between what is known and what is not yet known, drawn in enough detail to show exactly where the next questions live. The unknown is not a wall, it is a door. And the fact that we can point to it, name it, and describe its approximate shape is itself an extraordinary achievement. Voyager 1 is out there right now, alone, moving at 61,000 kilometers per hour through interstellar space, its signal taking more than 22 hours to reach the engineers still listening for it on Earth. Ocean sediment layers at the bottom of the sea are holding the radioactive fingerprints of stars that exploded 2 to 3 million years ago, patient and precise, waiting for the next researcher to core through them. New stars are forming this moment on the compressed outer wall of the local bubble, collapsing from the debris of ancient explosions into suns that may one day warm worlds of their own. Standing at that frontier is not a dead end. It is an invitation. Every answer pulls the horizon back and reveals a deeper question. Wider, stranger, more worth asking than the one before it. Perhaps that is what the universe has been communicating through all of it, through the layers and the explosions, through the oscillations and the extinctions, through the 4.6 billion years of violence and chemistry and improbable stability that produced this planet and the life on it. Nobody here is a stranger. We are not visitors observing the universe from outside. We are a part of the story that has been telling itself for 13.8 billion years. And the story is not finished.